Hi, so we'll be learning about virtual memory and page faults in operating system today. So as you can see here, there is a main memory here, okay, and it is divided into multiple uh, fixed size of partitions called frames. So there is a space for only 3 pages, and your program is stored here in the disk, and you can see the program is divided into 4 pages. So now if you try to open the program, then this program will try to load in main memory. But since there is a space for only 3 pages and the program is divided into 4 pages, the program may not be able to open in the main memory. So this was the issue that larger programs were not able to load into main memory, were not were not load were not able to load into main memory. So therefore the concept of virtual memory was introduced. So virtual memory is nothing but to load only those page to load only those pages which are demanded by the CPU. Okay, which are demanded by the CPU. So now this case, when you try to open a application or program, then as you know, in a program, not all the instructions are readily required. So for example, if you click on a button, then what should happen? The instruction for that scenario may not require to open the app. Okay, so therefore, various instructions, or you can say various pages, may not be readily available or required to run the program. So only few pages will be loaded at first into the main memory. Okay, so this is a concept called virtual memory. So now let's consider a scenario in which there is a disk and your process is stored here with page 0, page 1, page 2 up to page 7. So these are the 8 pages of a process. Okay, and now there is a main memory. Okay, your main memory has the space for only 4 pages. Okay, for only 4 pages. Then comes there is a page table. So page table, as you all know, is required to know that the page is stored in which frame. Okay, so this is your frame 0, frame 1, frame 2, frame 3. Okay, so now initially this was the scenario. All the pages were in the disk. Okay, and your main memory is empty. Uh, so now user tries to open it, and the page 1 is brought in frame 1. Okay, page 0 is brought here. So in the page table, so this is page 0, page 1, page 2, page 3, page 4, page 5, page 6, page 7. So now P0 is in frame 1. Okay, so this is frame 1 and this is valid. Okay, so there is a column called frame number, and then there is a column called valid bit. Okay, this tells if the frame number stored here is valid or not. Okay, let me also write it down. What does valid bit tells? If the frame number is valid or not. So now let's say page 2 is brought here in frame 3, page 2, and similarly other pages, let's say page 4 and page 5 are brought here. So now let's also write them down. So page 4 is in frame 0, page 4 is in frame 0, this is valid, and page 5 is in frame 2, page 5 frame 2, this is also valid, page 2 frame 3, page 2 frame 3, this is also valid. Initially all the valid bits were marked 0. Now why is this so useful? Because you can see that there is still some information stored here. Okay, there is still some bits are there. Okay, some zeros or ones. Okay, so frame number is also like zeros and ones. So there is some garbage value stored here. Okay, so again, you can, everything is stored in your computers are in the format of binary. Okay, so if I do not use the valid bit here, okay, if I do not use it, then how do I know if this is a garbage value or not? Therefore, whenever a page is brought in main memory, then we also mark if that frame number is valid or not. So to differentiate between a valid frame number and a garbage frame number. Okay, so that is why it is required. So now, as you can see, only P4, P0, P5 and P2 are in main memory. Where are other pages? So P1, P3, P6 and P7, they are still in disk. Okay, and your program is perfectly running. Why? Because uh, to run the current state of the program, only P4, P0, P5 and P2 pages are required. So now let's say user does an activity, or by any means P1 is required. Okay, P1 is required. So so now let's see. So first step is CPU request P1 page. Okay, so now it will refer page table. Okay, and as you can see here, in the page table P1, the valid bit is 0. So he, as you can see here, check valid bit for page 1. Okay, and since valid bit is 0, that means the fifth step, uh, page has to be brought into main memory. Okay, from disk. So now this particular thing is called page fault. That means page wasn't found in the main memory and it has to be brought into the main memory. Uh, so now uh, now there are two scenarios. Now one scenario is, so first scenario is, there is available space. There is an available space in main memory. Okay, so for example, if this was your main memory, okay, and this was filled, this was filled and this was filled, this was available, so then that page will be brought here. Okay, so then there is no issue. Now there is a second case in which all frames all frames are occupied. All frames are occupied in main memory. Okay, so now here in this case, uh, so first step will be, you will put back the page from main memory to disk. Okay, so why is this required? As you can see here, so as you can see here, this is your main memory, and let's say CPU requested P1. So CPU requested this P1 page. Okay, so now this P1 has to be brought in main memory, but it has to replace one of these pages. Okay, so if it try to replace P4, then P4 must be brought back to disk, and P1 will then take the position of P4. Okay, so first step is put back the page from main memory to disk. Which page? The page which needs to be replaced. Okay, needs to be replaced. And second thing is, bring the new page into main memory in the position of page replaced, in the position of page that is replaced, that was replaced. Okay, so So now you can see that the second condition is really expensive in operation because it needs to replace the existing page with the new page that is requested by the CPU. So that is what we call page fault. Okay, and it requires it some time to bring the page into main memory and do the action. So that was all about page fault.